In this lecture, I'm going to be talking about quasars, which is one of my favorite topics in all of astronomy. This is actually what I did my research on both when I was an undergraduate and in graduate school. This is what I did my master's thesis on. So this is one of my personal favorites. And one of the reasons I got into quasars was because I like black holes, and I said, well, I want to know about the biggest black holes there are out there. And the biggest black holes that we have ever discovered are in what are called quasars. Those ones that I mentioned in the previous lecture that are 2 billion or even 10 billion times the mass of the sun. They are supermassive black holes, and they're in the center of galaxies, but they're only certain ones, and they're called quasars. Now, quasars are part of a more general category called active galactic nuclei. They all involve supermassive black holes, and there's just sort of variations in the properties of the galaxy and of the black hole that affect how these things are classified. So you'll also hear this term, but I'm going to stick with quasars. The one you see in this picture is called 3C273. This is the one I actually did my master's thesis on, and it was the first quasar that was ever discovered. This is back in the 60s or something. Now, as you can see, if you look at it, it looks pretty much like a star, except there's this sort of junk over here. You might even wonder if that's real or if that's just some mistake in the telescope or something. That is real, as it happens, but basically this thing looks like a star. However, when they looked at this same thing in radio waves, they found out that this thing gives off radio waves, and stars don't do that. There aren't any stars that give off radio waves. So the name comes from the fact that it is quasi-stellar. It looks like a star, but it's not a star, so it's quasi-stellar, and it's a radio source. So the short version of quasi-stellar is quasar. Another thing that was discovered pretty early on about these guys was that they have enormous redshifts. In fact, they're so redshifted that when the first people, the spectrum of this thing, they were like, I don't even recognize that. It looks so different from what I would expect. And this is just to sort of give you a sense. Here's the spectrum of 3C273 lined up with like a theoretical one. And you can see, for instance, this is where the H beta line is supposed to be. That's the transition from 2 to 4 in hydrogen. And it's not there. It's all the way over here. It was so redshifted that people couldn't even see the lines they were expecting to see. But a guy named Martin Schmidt did realize that what was going on was just that there was a gigantic redshift. In fact, more redshift than anything they had ever studied up until that time. So, just to give you a sort of compare and contrast kind of thing on quasars versus stars, this will help you think about the characteristics of quasars. So we already said they look like stars in visible light. And quasars give off radio waves and stars don't. Quasars have a high redshift. Stars, if they have a redshift, are pretty small. If they have any shift at all, it's small. We'll find out in the next unit that having a high redshift is actually a consequence of it being extremely distant, way outside the Milky Way. Whereas, of course, stars are relatively close. They're inside the Milky Way. And quasars actually give off so much light that they are brighter than their entire galaxy that they're sitting in. Whereas stars, compared to a galaxy, don't have very much luminosity. Quasars also turn out to be very, very small. How we discovered that you can read about in your book. But quasars are very small, and yet they give off more light than entire galaxies. And we know that they have to be that luminous because they're so far away and yet still have a very high apparent brightness. So how do we explain this? And it really took a long time for astronomers to come up with a way to explain this. It took decades for them to come up with any ideas at all. But by the 80s and 90s, they had a pretty good idea that this was being caused by black holes. And this is another sort of little line of evidence. You remember that sort of squiggly thing that I showed you? This is another quasar, and it's also got something like that that seems to be shooting out of it. Most quasars, you don't see anything like this in visible light. 3C273 and M87 are kind of exceptions, but you see this a lot in radio waves. You see these thin things shooting off of the quasar, and these are called jets. And they found out that these jets are moving at ridiculously high velocities, like near the speed of light. In fact, when you measure it, it actually looks like it's more than the speed of light, but they figured out that that was kind of an optical illusion. That was a big thing I did in my undergraduate research, was studying the optical illusion that makes them look like they're traveling faster than the speed of light. So this is another thing that we have to explain. We have to explain that high luminosity, very far away, very small, and giving off jets. Here's another picture of the jets, just to give you, this is a different one that's sort of zoomed out. This is called Centaurus A. This is a radio picture in the background here. Down in the middle, you have this bright spot that's like the quasar. This little box right here shows you what you would see in visible light. So, bright spot, you don't see all of this exciting radio stuff. These thin lines going off are the jets, and out at the ends, they end in what are called lobes, with these really hot spots at the end. So it's like the jets are shooting stuff off of the quasar and then making these big clouds out in space 100,000 light years or more away. Basically, 100,000 light years is huge. The entire Milky Way is smaller than that. So these lobes are gigantic. So whatever is powering this must be extraordinarily powerful, too, to account for pushing material at near the speed of light out to hundreds of thousands of light years away. So this is sort of the picture. Basically, these are the biggest supermassive black holes in other galaxies. So 2 billion times the mass of the sun, even up to 10 billion is the most massive that we've got now. Now what happens is that supermassive black hole is, of course, sucking stuff in. And the stuff that's orbiting it is going at very, very, very high speeds, because there's a lot of gravity caused by a black hole that's that big. And so it's going at very high speeds. That means it gets very, very, very hot, and therefore it's going to give off a lot of light. This stuff that's getting sucked in is called the accretion disk. Accretion means gathering stuff together, which is what the black hole is doing, and it happens to have the shape of a disk. And so we think most of that luminosity is coming from this stuff that's getting sucked in. The jets will be material that gets caught in the magnetic field of the black hole. Black holes do have magnetic fields, and it's strongest along the poles, just like anything else, like the Earth or like pulsars or whatever. Some of the gas gets caught in the magnetic field before it actually crosses the event horizon, and so it starts swirling around in the magnetic field, and it gives off radio waves. What we see depends on the angle. You can imagine if we're sitting down here and looking at it, we might not even see a jet because we're looking straight along the jet. Whereas if we were sitting over here, we would be able to see the jets, and we might be able to see the lobes out at the end. A black hole is the only thing that's strong enough to power these jets and make the lobes and also produce enough luminosity from its accretion disk. This is the only thing. This was considered pretty much a very strong hypothesis at the time I was studying it, but it was right around then that they first discovered and found really, really strong evidence of the black hole at the center of the Milky Way. And once we said we've got black holes at the center of the Milky Way that are supermassive, well then, this hypothesis became much, much, much more likely now that we have strong evidence in favor of the existence of supermassive black holes. So this is just the extreme variation. The Milky Way doesn't have this because our black hole isn't big enough. Some galaxies, the galaxies that have quasars, are because they have much, much, much bigger black holes in the center. And just to show you, at about the same time as all this, again, while I was sort of in graduate school, we got our sort of first view of one of these kinds of things. This is a zoomed out view of this galaxy NGC 4261 from the Hubble, well, this is from a ground-based one. This is the optical image, and those are the jets and the lobes that you see in radio. So the scale is about 85,000 light years. And then they zoom in on the center to a few hundred light years, and now you can kind of see a disk, maybe the beginnings of the jet there, and down there in the middle is where the black hole is. So we feel pretty strongly about the existence of these kind of disks now. We've even imaged one directly with the Hubble Space Telescope. So these are the most extreme black holes in the universe.